Start? Yeah. Okay. Hi. Good morning, everyone. So I'll just pick up where I left off yesterday. Just tell me, interrupt me anytime if anything is unclear. So let me just do a quick, 1-minute review. We introduced the concept of the fundamental concepts of game theory, which is composed of 3 ingredients: players, strategies, and payoffs. Defined Nash equilibrium, and then we saw a few paradoxical predictions of Nash equilibrium, including in the half the average game that we played as an experiment in this session. And then started to talk about alternative solution concepts to Nash equilibrium, and I talked about a level K model very briefly, but then moved on to something called sampling equilibrium. And today's talk is going to be mostly about sampling equilibrium, both with regard to empirical applications of it and its fit with experimental data, and how one might generalize the idea to look at repeated games, which create new opportunities and demands. Okay, so let's very quickly, I'm going to skip through this, we did it yesterday. Let's quickly just overview what we mean by sampling equilibrium, and then I'll do an application just to see how it works, and then we'll move on to experiments. So let's take, the idea can be applied to asymmetric games, multiplayer games. It's not a problem, but it's just easiest to explain it in the context of 2-player games. So let's just go through that one more time. So take a symmetric 2-player game with M pure strategies, and I'm just going to call them actions, because when I get to repeated games, strategies are going to depend on actions that are taken in a sequence of periods. So let P be a probability distribution over these actions, right, which is a mixed strategy. The likelihood with which actions 1 to M are played. And suppose that each action is sampled once. So suppose that my opponent is playing this mixed strategy, right? You can interpret it as my opponent is drawn from a population in which a proportion P1 is playing strategy 1, action 1, P2 is playing action 2, etc. But you don't need to interpret that way. Just suppose that I play this game, I try each of my M actions once, and my opponent every single time is an independent draw from this distribution P. Okay? Okay. Let Wi of P denote the probability that action I results in the highest payoff. When I collect the payoffs, I'm going to collect M different payoffs, right? When I sample action 1, I'll get a payoff, 2, I'll get a payoff. I'll get M numbers, which are the payoffs from my samples of these M actions. And the idea is that I'll look at the one that did the best, right? And I'll pick that one. And Wi of P denotes the probability with which action I ends up being the best, right? So given that my opponent is playing from a mixed strategy P, is using mixed strategy P, Wi tells you the likelihood that action I is going to win this competition, this sampling competition. Is going to end up giving me the highest payoff. It may or may not. I mean, all kinds of things can happen when I sample, but Wi denotes the probability with which action I actually ends up with the highest realized payoff. And a sampling equilibrium is defined by the equality for every I between Wi and Pi. So the likelihood with which an action is played in the incumbent population, which is given by P, if that matches the likelihood with which action I wins under the sampling procedure, that is called a sampling equilibrium. So that's just an overview of what it is. And we had an interpretation whereby this can be viewed as a steady state of a population in which if an action wins frequently through the sampling procedure, more so than it is represented in the population, it's going to increase its representation. So that dynamic process can be used to justify this. This will be a steady state of that dynamic process. Okay. Okay, so let's, this is something I skipped yesterday, but I'd like to go through because, it's a very sort of, although this concept has been around for 20 years, it's novel to most people. So it's just worth going through a simple example to just see how a sampling equilibrium is actually computed. Yeah. Yes, correct. Yeah, that reasoning will take you to Nash equilibrium. We've already seen that Nash equilibrium has certain properties. So this does not assume any knowledge of the payoff matrix or the payoff function. This is a different approach than the Nash equilibrium approach. But if I am aware of the payoff function, the set of players, if the entire game is transparent to me, then yes, for any given P, I can just calculate what's my best action, my best response. And actually, that's the reasoning which underlies Nash's existence proof, that if you think about the best response to P and then the best response to that and so on, this best response correspondence has a fixed point. That's Nash equilibrium, actually. So yes, if I knew, yes, forget about that and just travel with me a little bit in this world where I don't know. I just try out my actions and I try to see what works and I pick what works. Okay? Okay. So let's just see how it is computed in a particular example. So this was the all-pay auction example from yesterday. And if you look here, so just to remind you of what the payoffs, remember there's an object which is worth 5/2, right? That's 2.5. If I win this object, that's the value of that object to me. And I have to pay what I bid. And I have to pay what I bid regardless of whether I win or lose. That's the rules of this all-pay auction, okay? So for example, if I bid 1 and my opponent bids 2, then I'm going to lose. What will be my payoff? My payoff will be -1 because I don't get the object, but I have to still pay my bid, right? What will be my opponent's payoff? It will be 1/2 because they bid 2, they won the object for sure because I did not bid 2, I bid 1. So the opponent wins an object worth 2.5. They have to pay their bid, which is 2, and so the surplus that is left is 1/2. That is how each cell is populated in this matrix. Okay, so that's the underlying payoff structure. You're absolutely right. If I can look at this payoffs, if I know that my opponent is playing P1, P2, P3 over here, I can figure out what's my best response. Sure, I can do that, right? And it will depend on P, of course, but we're not taking that approach. Okay, yeah. If it's a tie, then it is one exactly. It's a coin toss, and so for example, suppose that we both bid 2. Suppose we both bid 2. Why are these payoffs negative over here? If we both bid 2, there's a tie. Then I get the object of 5/4 with probability 1/2, right? 1/2, which is 5/2 with probability 1/2. I have to pay 2, right? So if I could get that object. So it's 5/4, which is this is the payoff I would get if I bid nothing. So if I subtract my bid from this 5/4, I'll get this -3/4. Yeah. That's how these payoffs are determined. Okay. So now I told you yesterday that this is a Nash equilibrium. You can verify that if my opponent chooses this mixture, 1/5, 3/5, 1/5, then my best response includes this mixture. I mean, actually, my best response can be any probability distribution. You can verify that. But if I were to choose 1/5, 3/5, 1/5 also, then changing my choices is not going to improve my payoff, right? My expected payoff is going to be the same if I were to choose this, conditional on the fact that my opponent is choosing it. That's the definition of Nash equilibrium, okay? Now let's see if the sampling equilibrium in this game matches the Nash equilibrium. I'm not going to compute the sampling equilibrium, but I want to show you that it doesn't match, although it may be close. But it doesn't match it. So how do we verify? Suppose we wanted to ask this question, is the Nash equilibrium of this game also, does it happen to be a sampling equilibrium? We know from yesterday that every strict Nash equilibrium has to be a sampling equilibrium. Is it true for this? This is not a strict Nash equilibrium, right? It's a mixed strategy Nash equilibrium. Is it a sampling equilibrium? How can we verify it? Okay, all right. So how do we verify it? We say, okay, suppose my opponent is choosing 1/5, 3/5, 1/5. What is the probability that when I sample this, the likelihood that this will win, the sampling procedure, is exactly 1/5. That is the condition for sampling equilibrium. The condition for sampling equilibrium is if my opponent is playing from this mixed strategy, and I sample and I pick the one that wins best, I pick the strategy that wins, that gives me the highest realized payoff, the likelihood that this strategy gives me the highest realized payoff should be exactly 1/5. For this to be a sampling equilibrium. That's the meaning of sampling equilibrium. So you can see the difference with Nash. Okay, it's not a best response-based reasoning. Okay, so let's try to calculate it. So the first thing so let's calculate what is the probability that action 0, or the bid 0, is going to win, is going to give me the highest payoff if I sample 0, 1, 2, and my opponent is choosing a mixed strategy based on these probabilities. Okay, we can calculate that. How do we calculate that? Well, what are the events that must occur for 0 to actually give me the best payoff? When I sample 0, I could either get 5/4 or 0 or 0. Those are the 3 payoffs that I could receive, right? If I get 0 here, and then when I sample this, I get this, and then when I sample this, I get 1/2, then strategy 0 will not win. So that's an event that will not result in my selection of bid 0. So let's try to identify events that would result in my selection of 0. So how can 0 win? The sampling procedure. When I sample 0, suppose I get 5/4, okay? And when I sample 1, suppose I get less than 5/4. And when I sample 2, I get also less than 5/4, then 0 will win, right? So that's one possible event that can result in my selection of 0 under the sampling procedure. So let's calculate the probability of that. Probability of getting 5/4 when I sample 0 is exactly 1/5. Right? My opponent has to pick 0, I pick 0, I get 5/4. Okay? But now when I sample 1, I cannot get this because then 0 will not win. So I must get either 1/4, which is less than that, or -1, which is less than that. Correct? So one way in which 0 could win the sampling procedure is, when I sample 0, my opponent plays 0 and I get this payoff. When I sample 1, opponent plays either 1 or 2, and I get this payoff or this payoff, which is lower than 5/4. And when I sample 2, it doesn't matter. It doesn't matter. Right? If I get 5/4 when I sample 0, then there is no way for me to beat that when I sample 2. Is that clear? So one way in which 0 can win the sampling procedure is I get 5/4 when I sample 0, I get one of these two things here. So my opponent chooses 1 or 2 when I sample 1, and anything can happen when I sample 2. What's the probability of that event? It's going to be just 1/5, because I need this to happen, plus 4, multiplied by 4/5. Remember, these are independent draws from the population, multiplied by 4/5. So 1/5 times 4/5 is the probability that I will get 5/4 when I sample 0. I will get either 1/4 or -1 when I sample 1, and I'll get one of these three, doesn't matter what, when I sample 2. Okay? It's a possible event, right? There's a probability with which this event occurs. 5/4 here, 1/4 or -1 here, and then anything here. That's just an event. That's right. The event requires my opponent to take a particular action, right? And there may be other events that also cause 0 to win. Okay? There's one more way in which 0 can win. What is it? There's one other event that will lead 0 to win. When I sample 0, 1, 2, there's another way, another completely different event that could happen that still results in the highest payoff being from my bit 0 than from bit 1 or bit 2. What is that event? When I sample 1, I get. When I sample 0, no, we've already done that. When I sample 0, I get 5/4. When I sample 1, I get this or this. When I sample 2, I get anything. This is the probability of that event. There's a completely different event. When I sample 0, when I sample 0, I get 0. I can still win. When I sample 0, I get 0 because my opponent does 1 or 2. Correct? Okay. Now when I sample 1, I must get less than 0. Opponent plays 2. Yes. When I sample 1, opponent plays 2. When I sample 2, opponent plays 1 or opponent plays 2 again. Yes. Right. So what is the probability of that event? I also have to add, because that's another way in which 0 can win. Right? So this kind of reasoning is just to show you exactly how sampling equilibrium is computed. You know, how you can actually approach the thing. Because if it's a novel concept, then you can write down the definitions, but it doesn't become tangible until you try to compute the thing. But this is the process by which you compute. Okay? All right. So what's the probability of the second event? Second event, the probability that I get 0 when I sample 0 is what? No, it is 4/5, right? It's 4/5. My opponent can choose either 1 or 2. Yeah, it is, probability of this is 3/5, probability of this is 1/5. Right? So with probability 4/5, I'll get 0. With probability 1/5, I'll get 5/4. That 5/4 I've already done. Okay, but now I'm looking at a different way for 0 to win the sampling procedure. Right? So when I sample 0, I can get 0 with probability 4/5. With probability 1/5, I'll get 5/4. With probability 4/5, I'll get 0. Is that clear? When I sample 0. Okay. When I sample 1, it is, in order for 0 to win, I must get this outcome. And the probability of that is 1/5. Then when I sample 2, I must get this outcome. Again 1/5. So the probability is going to be 4/5 times 1/5 times 1/5. And that's it. There is no other way for 0 to win the sampling procedure. So now it's a very simple thing. We just add up these probabilities and you get 24 over 125, which is not equal to 1/5, which proves, it doesn't tell us what the sampling equilibrium is. It tells us it cannot be the Nash equilibrium. Cannot be, because Nash equilibrium is slightly different from this, right? It's 25 over 125, okay? Now, this doesn't mean that the sampling equilibrium is close to the Nash. This is just a negative argument that cannot be equal to the Nash. What it is, we don't know from this exercise, but at least we have verified that there's a difference between sampling and Nash in this example. Right? The reason the value of going through this is not to show you that there's anything deep about sampling equilibrium in all pay auctions. Value is, what are the steps that one must take to compute sampling equilibrium, so that the concept itself becomes a little clearer. That was the goal of this exercise. Are there any questions on this? Okay. So now we can move on to the questions that came up yesterday, which were, okay, what about the predictive? When Nash and sampling give us different predictions, which one does better, right? So let's move to that. Okay. So this game we saw yesterday, I'll skip through. Okay, now just a reminder that in many games, there will be multiple sampling equilibria. In fact, in this game yesterday, there are multiple sampling equilibrium. There's the one where L is chosen with probability 1, and then there's the mixture, 20%, 28%, 50%, roughly speaking. These are two different sampling equilibria, and yesterday I made the argument that if you write down a dynamic process that, the likelihood, the frequency with which a strategy is used increases if it wins the sampling procedure with greater probability than it is currently being played, then it starts to be played with greater frequency. So this is a disequilibrium dynamic process. A rest point of this process, right, whenever all the p's are not changing, has to be sampling equilibrium, because for every I, the likelihood of winning is equal to the likelihood with which it is being played, right? So the rest point of this dynamic is clearly sampling equilibrium. And then stability, stability with respect to this. So, it's a dynamic process. So, you can have sampling equilibria that are unstable under this dynamics, others that are stable, and you can use that as a equilibrium selection criteria for sampling equilibria. And then you can ask, for example, in this game, for example, in this game, which one is stable? And it turns out that, somewhat surprisingly, at least for me when I first saw it, this is unstable, this one is stable. So it allows you to select between sampling equilibria. The next thing that I'd like to do is to give you predictions where sampling and Nash give you very different predictions, and then compare them to experimental data. Okay, and I want to talk about a paper. This is joint work with Juan Camilo Cárdenas, César Mantilla, and we are looking at now what does sampling equilibrium tell us compared to Nash equilibrium in what are called common pool resource games. This may be familiar to you. I'm just going to go through the model. A common pool resource game, and this was developed and studied by several people, but most notably Elinor Ostrom, right, who the late Lynn Ostrom, and her collaborators, because there was a lot of literature. There still is around what's called the tragedy of the commons, that commonly owned resources will be depleted and destroyed, and she was finding empirically that sometimes that's not the case, and that they're sometimes preserved and sometimes not, and she spent really a lot of her career trying to understand when they are destroyed and when they are not. And I want to show you that in this kind of game, when you do an experimental treatment in a lab, you give people payoffs that resemble those that would arise in a common pool resource setting. The Nash and sampling equilibria give you very different predictions. Stable sampling versus Nash give you very different predictions. Then you can see how do experimental subjects respond, which one seems to do better. And there we will have a comparison not just between Nash and sampling, but also between quantile response equilibrium, which came up yesterday also. Okay, so here's a common pool resource game. So it's a sort of stripped down version of what a common pool resource situation entails. What's a common pool resource? Think of grazing lands or forests or fisheries, inshore fisheries, where there's a set of users, a bounded finite set of users. So others can be excluded, but there's a set of users. For example, there may be commonly owned village lands, and these exist, they exist for example, in Switzerland, you have got commonly owned grazing lands, you've got inshore fisheries in Brazil, and so on and so forth, and forest areas that are village called forest areas in India, and so on. So people in the community can use these freely, right? They may be either informal norms or actual state policies that preclude others from coming and using them, but you cannot prevent your neighbor from doing it, okay? And this game is supposed to capture that kind of environment. So how does it work? So you have n players, you have a set of actions. The set of actions now you should think of as extraction levels. How much time and effort do you spend taking fish out of the water or taking wood out of the forest, right? So the higher the action, the more the more intensively you're exploiting this common pool resource. And the more intensively you exploit the common pool resource, the more damage you're doing to others, because it makes it, it makes their returns from the resource go down. Because common pool resources are not public goods. They are, privately appropriated, right? The fish that you take out is no longer available, which might benefit other people as well as yourself. When you take fish out, when you take wood out, that is not available for somebody else. Okay. All right. So think of these as extraction levels, and let X denote, let Xj denote the extraction level of player J or individual user J. And we can add up these extraction levels, and you get an aggregate extraction level X. The payoff to a given player, let's call that player I. So Xi is the extraction level of player I, X is the aggregate extraction level. The payoff to a player depends on the own extraction level and also on the aggregate extraction level. So this is a payoff function where, it really doesn't matter who has done the extraction. If there's a lot of extraction, it doesn't matter whether it was my neighbor on the left side or my neighbor on the right side. The damage to me is the same. That is, this function is written in that way. It's referred to as an aggregative game sometimes, that where my payoff depends on what I do and the total sum of what is done, not exactly who is doing what. Okay, so it's a simple game. Yeah. No, this is not the damage. This is my total payoff, including my net benefit. So I benefit from taking out the fish, but the damage is from how much other people fish are taking. Yeah, the same. Yeah, for simplicity, just in the experimental tests that I'll show you, the game is set up so that each experimental subject is symmetrically placed. So I'm giving you this. It need not be. In reality, of course, it need not be. Some people may be more dependent than others. Some people may be very good at fishing, and yes, of course, there are asymmetries in real life. We're looking at a stripped down version of this that can be tested in a lab setting, right? Yeah, exactly, congestion, yeah. But I think then again, you could still make the point that, one person needs to go to hospital and the other person is just going for a vacation. You could still bring asymmetries in, but you're right, yeah. Exactly. Congestion is the right way to think about this, because the more people who are extracting the fish, the longer you have to wait to get a fish. The density of fish goes down, yeah. Yeah. So in this case, there's a divergence between individual incentives and collective incentives. G is increasing in the first argument. When I spend more effort fishing, I get more fish. No question. Conditional on how much is being extracted in total. But when the extraction total goes up, holding constant what I'm taking, it hurts me, because the more fish other people are taking out, the more time I have to spend for each fish that I catch. That's the idea. Okay? All right, so let me talk about two experimental treatments. One is Lynn Ostrom's classic work. This is an amazing paper, actually, Covenants With and Without a Sword, and that's, they look at various things that I won't have time to talk about. They look at the effects of communication and so on, and punishment. But I'll just talk about the basic results for the common pool resource game that they have here. And then, my friend and colleague, Juan Camilo Cárdenas, tried to do something similar, and we'll look at the experimental results that he got, and they're actually quite similar, and other people have done it. So what I'm presenting you with regard to experimental results is not my own work, but it's pretty consistent across studies. Okay, how do subjects actually play this game? It's simple, but it's also pretty complex, because you have lots of different. So let me just show you. How the experiment is conducted. So you get n experimental subjects. Each person is given an endowment E. You can think of these as tokens. So each person has a token. They're not told it's a common pool resource game or anything. They're just given some actions that they can take. They're given a payoff function, in a particular form, and they just said, okay, do whatever you want. So each person gets a total number of tokens, call it E, okay? And they can divide them between two markets, right? So one market is a private market. So you can think about, if you think about E, so Xi, suppose Xi is 0, that means they're not extracting anything from the common pool resource. Then they're entirely putting all their time and effort into what you can think of as a private market, a regular labor market where they get a wage W. So basically, so for every token that they put into the sort of normal standard labor market, they get W. So if they put all the tokens into this market, they'll get W times E. Okay? Now what is Xi? Xi is the amount that they are not putting into the labor market, but they are putting into the common pool resource. So you can think about somebody who can either spend time working in a market-oriented job, or spend time extracting forest resources or fisheries or grazing cattle on a common field, etc. What do they get from the common pool resource? That's the second part. So you look at how much total extraction is being taken. So how many tokens are put into this sort of common fund, if you like, right? That determines the total amount X, that's Xi added across all the individuals I. F of X tells us the total amount of output that can be appropriated from this common pool resource. And you should think of F as a concave function. The more effort is put into the common pool resource, output will go up, but it will go up at a decreasing rate, right? So the marginal returns to effort go down, right? So the extra value of putting more resources into the common pool resource go down as you put more and more and more. This is very standard in fisheries and forests and so on. How much do you get of the total? The amount you get of the total is your share of total effort in the common pool resource. So somebody who spends 6 hours fishing will get twice as many fish as somebody who spent 3 hours fishing. That's what this says. Okay, but if they both reduce their fishing to, instead of 3 and 6, they reduce to 1 and 2, they will still get, the one will get twice as much fish as the other, but the total amount of fish caught will of course go down. The total amount will go down, but the total amount caught per hour of fishing will go up. Because there'll be greater, it'll be easier to catch fish because there's less intensive exploitation of the resource. That's the idea of this function. Okay, I won't give you the actual function that's used in the experiments, but I'll tell you roughly what it qualitatively looks like. So these were the two studies, the subjects per peer group. So Cardenas had 5, n equals to 5, n players. N is 5, and Ostrom and Walker and Gardner had n equals to 8. They played this over 10 rounds, so it was a finitely repeated game. I'll talk about repeated games a bit later, depending on time. But they make these extraction decisions not just once, but 10 times, right? So they make an extraction decision, they get payoffs, they do it again, they get payoffs, and they do it 10 times. And we can compare what their actions look like at the end versus the beginning. Okay? So now you can already think that in the first few periods, they could be sampling. They could be trying out different actions, seeing what the payoffs look like. Because it's quite a complicated game, actually, from the perspective of an individual who hasn't, seen this before. The action set, so this is just E. This is the total number of endowments. But what can you do? The action set is 1 to 8 in Cardenas and 0 to 10 in Ostrom. So in Ostrom, you can either put your full 10 tokens into the private labor market, in which case you'll get 10 times W. Or you can put all the 10 tokens into the common pool resource, or you can split them in any way you like, 5, 5, and 5. Can you repeat that? The payoff function depends on the actions of everybody. Oh, if everyone's putting 0, you've got 0 over 0. Yeah, f of 0 is 0, right? Yeah. And you define f of x over x as 0. Yeah. That's right. Yes. People are not given a function. You cannot give functions to people in the lab. That doesn't mean anything. They are told, if your extraction is 3 and the aggregate extraction is 17, this is what you get. So they get this big table, which is actually the computed values of the function at the relevant points. Right? The function is a continuous function, but of course, you have a discrete set of tokens. So they just get a big table that says, if you choose 5 and the total, all the others collectively choose 23, this is your payoff. But the payoff is coming from this function. This is underlying the payoffs. So they see this big set of numbers. And that's actually, to me, a right way to test sampling equilibrium versus Nash, because you can't just look at it and, it's not so obvious, to say, okay, this is the best way to play. It may be to some people or maybe not, but you just see this big set of numbers. So you see something like this. You see something like this, except that for you, you have got, for the Cardenas case, you have got, for your own actions, you have got 1 to 8. 1, 2, 3, 4. You can put 1, 2, 3, 4 up to 8. For the others, since there are 5 players, it can go up to 40, the aggregate, the capital X. So you get a 40 by 8 matrix. That's what you see. And you just see your payoffs. But it's coming from that function. And you just say, okay, play this game. And then you can learn if you like, because you play repeatedly over 10 times. That's the idea. Is that clear? Originally by Ostrom and her co-authors at Indiana University, and then subsequently by others, including Juan Camilo. Right? So that's the structure of the experiment. All right. All right, so let's go to, okay. Now the Nash equilibrium in this, I'm not giving you the actual functions. They don't look particularly enlightening, it's just functions. Or I'm not showing you the payoff matrix as either, but if you look at it and you compute the Nash equilibrium, in both cases, the Nash equilibrium is 8. So in the Cardenas case, the individually rational, if you want to maximize your payoff, you want to put everything into the common pool resource. Even though it's going to be damaging to other people, if you just only care about your own payoffs, you want to put everything into the common pool resource. That's the Nash equilibrium. And the efficient strategy is to put only the minimum amount, which is 1. So it's very much like that public goods game that I said. There's a tension between individual rationality and sort of collective payoffs, aggregate payoffs. In Ostrom, although you can put 10 into the common pool resource, the function f was chosen so that the Nash equilibrium turns out to be interior. It's 8. So actually, if everybody chooses 8, right, that's the Nash equilibrium in Ostrom. If you go higher, if you go to 9 or 10, you will actually get lower payoffs. That's the definition of Nash, right? Unilateral deviation should hurt you, or at least it should not help you. So the key point is that you have an interior equilibrium here, Nash equilibrium for Ostrom. This is a boundary equilibrium for Cardenas. And that is really, really important when I talk about comparison with quantal response. Because you can fit quantal response to these two games, the results, but using very different noise parameters. Whereas sampling equilibrium is parameter free. That's the case I want to make. And the optimal behavior that maximizes the aggregate payoff, if you just aggregate this payoff across all the users, is for people to exploit the resource less. So in Ostrom, 4.5 is the optimal, the group optimal level of extraction. And this is what people mean by tragedy of the commons, is that the individual incentive is to over-extract relative to the efficient level. 8 versus 1, 8 versus 4.5 in this case. Yeah. Yes. You'll have to change the game. So you have to, yes, if you put a tax on extraction, if you punish people for extraction, you can change the payoffs in the game such that you shift the Nash equilibrium towards that. That's basically what mechanism design is about, is to design a game in which the individual incentives and whatever it is, the social welfare function that you want to maximize, are brought into consistency with each other. But that's changing the game. Yeah. No, sorry, that is quantal response equilibrium. I spoke too soon. Sampling equilibrium does not involve any parameter. Nash equilibrium does not involve any parameter. Both these concepts are parameter free. Yeah. Yesterday there was yet another solution concept, quantal response equilibrium, that was introduced, and it's good that it was introduced because I will show you results of that. But that's, I have not even discussed that yet. So let's yeah. So what do the experimental subjects do? So here's what they do. So this is in the, if you just aggregate across, take the averages across the 10 rounds, And here, if you just look at the last few rounds after presumably learning has taken place, you don't get much difference actually. So what you do is you get this monotonicity. This is, so Juan Camilo showed me these results before we started to work together on sampling equilibrium. And I said, this looks like sampling equilibrium, just, based on what I knew about the public goods game. But it is certainly not Nash equilibrium. Nash equilibrium, so in the Ostrom results, you should get a spike at 8 and 0 everywhere else. Nash equilibrium, if everybody chooses Nash equilibrium, everybody should just choose 8 and there should be a 0 frequency with which other actions are chosen. Same with Cardenas. Cardenas, notice that Cardenas 8 is the maximum. So therefore, the white bars do not extend beyond 8. Right? Cardenas only goes from 1 to 8. Ostrom goes from 0 to 10. Right? And what you observe subjects doing is this sort of monotonic frequency where, at least in Cardenas here, you can see, yes, it is true that, the strategy that corresponds to the Nash equilibrium is played with higher frequency than these other strategies that are far away from Nash equilibrium. So that is true, and that's what makes you think actually of quantal response. But certainly it is not the case that people are just putting, just calculating and playing the Nash equilibrium. You might say, okay, in the early rounds, maybe they're just, they're learning the payoffs, and they're trying to figure out what other people are going to do, and so on and so forth. But even if you look at the last 3 rounds, you get this sort of, diversity of behavior. It's systematic. There's a probability distribution, but it's not random. You get this sort of increasing as you get, that there's a greater probability that people are putting onto actions that are close to Nash, but certainly there's plenty of probability put on other actions as well. Okay, include what? Yeah, it does seem that way. Yeah. Why do you? I don't know, because this is experimental data. This is not coming from any theory. This is the data that we want to match the theory to. Yeah. I'll show you sampling equilibrium. Yeah. So remember, with sampling equilibrium, every strict Nash equilibrium has to be also sampling equilibrium. In Cardenas, there is a sampling equilibrium which is exactly the same as Nash, but it is not stable. It is not stable. What we saw for that little 3-action game also applies for these games. And we can ask, well, what does the stable sampling equilibrium look like? If we knock out the unstable sampling equilibria and look at only stable sampling equilibria, do we get something that resembles these experimental results? You had a question? You mean instead of 10 do it for 20 or 100 or, yeah, we don't know. We never know. In experiments, you never know. Can't rule it out, but doesn't seem as if you're moving closer to Nash towards the end of these rounds as you are towards the front. And you might say, okay, you need to do it 100 times or 1,000 times, maybe. It's possible. It's possible. It's possible. I'm just telling you. What you're doing, I want to show you, is that you're getting pretty close to sampling equilibrium. You're not, it just happens to not be Nash equilibrium. I'll show you. Yeah. So let's compute the stable sampling equilibrium for these games and see what happens. So first, let's look at Cardenas. Cardenas was the one where the strategies were 1 to 8. So the top figure gives you 3 things. Forget about the gray, that is quantal response. I'll talk about that in a second. Forget about the gray. The black is what in this paper we call payoff sampling equilibrium, which is what I have described to you as sampling equilibrium. And the white is the data, experimental data. Okay? And the stable sampling equilibrium here, which is the black bars, at least qualitatively have the same pattern of behavior that you find in the realized experimental data. Now you can calculate the distance. You can calculate the distance between the 2 distributions, right, as a test of goodness of fit. And I'll show you. I'm not sure I have it on the graph, but it's pretty good. Certainly much better than Nash equilibrium. Nash equilibrium, you would have just a big spike at 8 and 0 at everywhere else. Huh? But you may not have converged? Yeah. Yeah. I mean, you can measure the closeness. However, quantal response can give you something very close. Now, what is quantal response? I'm not going to give you a formal definition, but quantal response is a way of sort of generalizing the idea of Nash equilibrium while allowing people to make mistakes. And the idea is basically, that given whatever the other person is playing, in Nash equilibrium, you are best responding to what they are doing, and they are best responding to what you are doing, right? That's in the two-player case, but the same thing applies more generally. Quantal response, you're more likely to play, given what the other person is doing, strategies that give you the highest payoff are more likely to be played than strategies that give you a lower payoff. Okay, in quantal response equilibrium. What makes it equilibrium is that you take into account that the other player also is making errors. So basically you're best responding not to what they intend to play, but rather what they will end up playing subject to the errors that are built into the process. Right? So there's a distribution that you're responding to, and that gives you yourself a distribution that you generate, and the consistency of these distributions is quantal response equilibrium. But this is where the parameter comes in. So with quantal response equilibrium, there's a parameter, a tunable parameter that can allow the predictions of the model to vary. And this tunable parameter at one extreme will actually give you Nash equilibrium if there's no errors. If there's no errors, you're just best responding to the other person, they're best responding to you. Nobody's making any errors. As you increase the rate of errors, if you take it to the other extreme, maximum possible errors, you will get a uniform distribution of actions. So quantal response equilibrium actually can explain just about, a very broad range of data, as long as you allow this parameter to vary, widely enough. It's a parameter. The error is defined as how close you are. So suppose that you are playing some strategy, and my best response is to choose, let's say, 2 in the auction. If the error rate, the parameter is high, then I could end up choosing something other than 2 with high probability. Basically, that if my best response to whatever you're doing is to choose 2, and the error rate is high, I may end up choosing 1 or 0. But I'll be more likely to choose 1 than 0, because 1 is closer to 2 than 0 is closer to 2. So that's the basic idea. And if the error rate goes to infinity, basically, if everything is error, then I'll just, basically, no matter what you're doing, I'm just going to choose randomly across my actions. So that gives you a lot of flexibility in fitting a quantal response equilibrium to data. And if you exploit that, you can get a pretty good fit. So this is quantal response equilibrium for this game, with the error parameter tuned in an optimal way to try to find the best quantum response model for this data. And there you see that it fits about as well as sampling equilibrium. So then somebody might say, okay, so why do we need sampling equilibrium? We can use quantal response. You just tune the parameter and you get this thing. And the counter argument that we try to provide in this paper is that if you look at these two experiments, this is the Cardenas experiment and this is the Ostrom experiment. Again, you see sampling equilibrium fits the data pretty well, but if you find the quantal response equilibrium with the parameter tuned optimally, you find a very good fit. But the parameter, the noise parameter for QRE here and the noise parameter for QRE here is an order of magnitude apart. You need to explain this, you need a very different error rate in QRE than here. And if you allow, because of that freedom to choose that parameter, that advantage can allow you to fit model by model by model, or experiment by experiment by experiment. But if you insist on using the same error parameter for a broad range of experiments, QRE does much worse than sampling. Yes, please do. Please do. Yeah, please. You could try that, but the difference between the fitted values of the parameters here, optimally fitted, is about an order of magnitude, 2 orders of magnitude. I'll show you. It's so large. I'll show you. Oh, where is it? I don't have it on the. Sorry, I don't have it on the. You can try that. We didn't try it. You can try it, but basically there's 100-to-1 difference in the error rate from one versus the other, and adding two actions is going to give you a sort of negligible change in that. That's my feeling, but you can try it. But that's the argument. I'm not saying that it's completely watertight, but the argument is that whenever you have more parameters, your model is going to be able to fit data better. And sampling equilibrium is hard to fit because it is parameter free. And that is one reason why Nash equilibrium is good, because that is also parameter free. Right? The problem with Nash is you don't get this prediction. Yeah. That's a good point. Yeah, that's a good point. You should end up with a you might say that the QRE should give you a different error rate if you fit to the last periods, 8 to 10, than the first periods. Yeah, we didn't do that, but that's possible. But the point is, when you have an interior Nash equilibrium like this versus a boundary Nash equilibrium like that, that's one of the things that's causing the fitted error rates to be very far apart. But yeah, whenever you have a free parameter, if you have more than one, you can do even better. The more parameters you have, you can always fit the model better. And what we're managing to do here, I think, with sampling equilibrium, is to fit the data with a parameter-free model almost as well as you can with a flexible parameter model. Yeah. Yeah. Yes, but nobody told the experimental subjects to have a distribution. I mean, Nash says that they shouldn't have that distribution. Yeah. Yes. I don't think that we are disagreed on this. The level of rationality required for Nash to be applied is demanding. And you might say, oh, with this big table, what should I do? I have to go, take care of a whole bunch of other stuff. Let me just pick something, even though I want more money than less, because these experiments are run with real money. At the same time, that just says that you got to be cautious in applying Nash. And if you're cautious in applying Nash, then what do? What's your alternative? I'm telling you that sampling is one possibility. That's yeah. Okay, so let me see. I have about 20 minutes left. So this is another paper with the same set of authors, but here we look at public goods games instead of Nash equilibrium. This is something I've shown you before, and this is not experimental. I just want to show you what sampling equilibrium looks like in public goods games. We've already seen a bit of this. What's a public good game? It's very similar to the common pool resource, except that when you contribute to the public good, instead of hurting other people, you are helping other people, right? So basically, the output that you create again, it is done with tokens. So you can put your token into a private account, or you can put it into a public account. If you put your token into a public account, it increases the total output. But instead of that output being shared by everybody in proportion to their investments, that total output is available to everybody without restriction, right? So the fisheries were the example of a common pool resource, and irrigation system would be an example of a public good, where if you contribute effort to a collectively useful irrigation system, the fact that it is there, or a road, even a road, if everybody can use it, it benefits even the people who did not put any contribution. That's not like fisheries. For fisheries, you got to sit there on the water and fish to get the fish out. Yeah? Okay, so here's a public good game. Similarly, you have your tokens, your endowments, 0 to E, and the payoff function. So the difference is that so instead of W, we just put 1. So basically, if any token that you do not invest, so A is your action from this set, E is your total number of tokens. Any token that you do not invest in the public good, it gives you 1 unit of a payoff. Okay. And any token that you contribute to the public good, the total contribution here is S, and here this F is different from the other F, right? But again, concave. Yeah? So it's just is a function of this. But the key thing is that you don't have the xi over x. So it's not as if this total output is divided among people. There's a certain amount of fish or timber or whatever livestock feed that people get in proportion to the number of hours they spend fishing or grazing. It's that everybody gets the benefit. Okay, so in this case, actually, contributions have a positive effect on others, in the common pool resource they have a negative effect. Okay, what does sampling equilibrium look like? Okay, so here's the type that is often tested experimentally. It's a linear public goods game, which is where mu is the parameter that tells you what is the value to other people of your contribution to the public good. And as long as suppose mu is less than 1, if mu is less than 1, that means every time I switch a token from private to public, so every time I take remember, a token that I keep is worth 1 unit. If I put it into the public account, it is worth mu units to everybody, including myself. So suppose mu is, let's say, 2/3. If I put it into the public account, I lose 1, right? Because it's not in the private account. But everybody gets 2/3. But I lose, actually, because from 1 I go down to 2/3. But actually I'm generating a lot of value for other people. So again, you get this tension between efficiency and equilibrium. Nash equilibrium in that case is going to say that people should contribute nothing, right? As long as mu is less than 1. Whereas efficiency, as long as mu is bigger than, as long as mu n is bigger than 1. So, if n is equal to, let's say, 3 players, and mu is equal to 2/3, then if I keep the token, it's worth 1. If I put it into the public good, it's worth 2. So it doubles the total surplus in the group. So efficiency requires me to place it there, but individual rationality requires me to keep it, right? Okay, so we're going to assume this. So if mu is less than 1, this is a social dilemma. It's like a prisoner's dilemma, but a little bit more general. If mu n is bigger than 1, it means that, remember, every unit that I put in there increases everybody's payoff by mu. So it increases the total payoff by mu n, right? If this is bigger than 1, then every token I put in there creates a greater benefit than I lose. But of course, I don't get the full benefit. And as long as mu is less than 1, I don't want to put it. If I'm just self-interested, I don't want to put it. Okay, so let's take this example. So this is a case where you've got 3 players, and you only have 1 token. Okay, very simple. It's like a prisoner's dilemma situation, a 3-person prisoner's dilemma. You only have 1 token. You either put it into private good or you put it into public. So if your contribution is 0, then you get 1, that token is worth 1 unit to you, 1 unit payoff to you. But assuming that others put nothing. If others put nothing, and I put nothing, then I get 1, and they will also get 1, right? They're all keeping their tokens. If I put my token and others put nothing, then I get mu, right? But of course, they also get mu, right? So we all get mu. And then if they contribute 1, basically, they collectively, this is the other 2 people together contribute 1. That means one of them contributes and one does not contribute. Then I will get my token because I did not contribute, but I get mu from the contribution of one of these other people. And if both of them contribute, then I get 1 plus 2 mu. That's how the payoff matrix is. Okay? So as long as 3 mu is bigger than 1, this is the payoff that we all get if we all contribute. As long as 3 mu is bigger than 1, then we should all contribute. We'll all do better if we all contribute. But as long as mu is less than 1, I always get more by not contributing than contributing, right? So this is the prisoner's dilemma feature of this thing. Okay. So if mu is less than 1, the Nash equilibrium has no contribution. If mu is bigger than 1, Nash equilibrium has full contribution. And most public goods games assume this. They assume the tension between individual rationality and equilibrium. And Pareto optimality, right? The efficiency equilibrium trade-off. Okay, we know that all strict Nash equilibrium are sampling equilibria. But what about stable sampling equilibrium? So if you think of a situation where the Nash equilibrium is this, right? That nobody contributes anything, everybody gets payoff 1. Whereas Pareto optimality requires that everybody contributes all their tokens, and then we'll all get 3 mu. For example, if mu is 2/3, then we'll all get 2. If we all contribute, if we all keep, we all get 1. So we can all contribute and actually double our payoffs, but it's not individually rational. All right, what about sampling equilibrium? So this is what I want to try to show you. Sampling equilibrium, especially if you use the stability refinement, gives you something very different from Nash. Okay, so here are three cases. So if mu is between 1/3 and 1/2, here you have the Nash equilibrium requires, so this is a probability distribution. So probability of non-contribution is 1, probability of contribution is 0. So think of Nash equilibrium as a probability distribution on these two actions. If I don't contribute, right, think of P1, P2, probability of contribution, probability of non-contribution in equilibrium. Nash equilibrium says don't contribute if mu is in this range, and don't contribute if mu is in this range. That's just the prisoner's dilemma aspect of it, right? Sampling equilibrium matches Nash if mu is small. Even though it is still efficient to contribute, sampling equilibrium does not give you contribution. So these two things give you the same prediction if mu is in this range. But if mu is in this range, Nash still says don't contribute. Sampling gives you a mixture, just like we saw yesterday in that 3-action game, except that this is two actions but 3 players. You get something similar to what we saw with 3 actions and 2 players. You get this mixture. What if mu is bigger than 1? This also came up yesterday. If mu is bigger than 1, then Nash actually says contribute, because there's no tension. If mu is bigger than 1, look at the payoffs over here. If mu is bigger than 1, even if nobody else is contributing, I get more if I contribute. Same here. Right? If mu is bigger than 1, same here. It's always better for me to contribute than not contribute. And Nash equilibrium then becomes full contribution. And Nash equilibrium in this case is efficient. But sampling equilibrium gives you another mixture. The mixture changes, it flips, but it's still a mixture. Which means that it's not efficiency that is driving the difference between Nash and sampling. In this case, sampling increases efficiency. In this case, sampling reduces efficiency. Right? I'm not going to go to the proof of the argument, but it's a dominant strategy. But remember, yesterday I gave you an example where dominant strategies are played with positive probability in sampling equilibrium. Remember, yesterday we saw this. Okay, so we saw this, and we saw that there's 2 sampling equilibria, and the stable sampling equilibrium has a mixture, and this mixture plays dominated strategies with positive probability, right? Now, yesterday you might have said, the reason why this is stable, right, is because the Nash is so inefficient. I can get much higher payoff if I play the other actions. So maybe the sampling equilibrium differs from Nash because there is some force in the process of sampling that is pushing me towards more efficiency. Better payoffs in the aggregate. What I just showed you says that that's not the whole story. that in fact you have here a situation where not only is full contribution efficient, which is also the case in the other 2 cases. Full contribution is efficient in all these cases. But here, full contribution is Nash equilibrium. So there is no tension between efficiency, and yet, sampling can drive you away from it. The fact that it's dominated, we know, is not going to be decisive, right? We know from yesterday. But the reason why that happens is not because of efficiency. In fact, for a long time I thought it was. But here's an example where you get sampling equilibrium is actually taking you towards inefficiency. Roughly speaking, what is happening is that, when I sample non-contribution, it is possible for me to do better. Imagine that mu is equal to 2. 2 is maybe too high, but if it's, let's say, 1.5, it's better to contribute than not to contribute. So if mu is 1.5, so what do we have here? 4.5? So it's much better for us to contribute than for us to not contribute. We will only get 1. It's also individually rational. How can sampling equilibrium push us away from this? Well, when I sample 0, it is possible that other people contribute, and so my payoff is 1 plus 2 mu. When I sample 1, I could get these 2 outcomes. And as long as that event has high enough probability, you can move away from the dominance. Should sampling? No, I'll tell you, yeah, it's a very good question. I mean, I can totally relate to your puzzlement because I myself was puzzled. This is not what we expected to see. In fact, we never even explored this case. Even though that the other case was familiar for about 15 years, we never bothered to look at this case. We thought it was an uninteresting case. In fact, experimenters very rarely look at this case. Because why bother? They assume that it's efficient, it's Nash, of course people will play it. Why bother to go to an experiment and spend all this money and time and effort? You'll get something that's not publishable because, it just gives you the obvious result. That's the logic, okay? We found 4 experiments that actually tested it. And you do not get this. You do not get this. You get something which gives you a mixture which puts higher weight on the Nash plus efficient strategies, but it is certainly not close to 1. And so the experimental literature, there's very little with this case. But even there, tentatively I would say that sampling should be taken seriously. So I don't think that I'm trying to tell you that you should ignore sampling and look at Nash in this case. Just because sampling gives you a bad outcome in this case doesn't mean that it's not a predictively useful outcome. And it can happen. So because there's such an important point, I just want to dwell on it a bit. Just give me 1 second. The idea is that when you're sampling, you don't know what is efficient, what is Nash. You know your actions. You don't know the structure of the payoff function. You're somehow trying out actions and trying to figure out what works and what doesn't work. And it is possible, even if you have Nash equilibrium and efficiency both telling you to contribute, if you knew the payoff function. When you sample non-contribution, you could end up better off than when you sample contribution. And if that happens with high enough probability, you'll be driven away from Nash. Yeah. For sampling equilibrium it is only ordinal. That is correct. It is not cardinal. That is correct. Yeah. Yeah. Yes, that is also a very good point. That within the range, as long as the reason why you get sampling equilibrium is changing here is because you are changing the ordering. Because basically it is purely, you remember, you're saying, okay, what wins? You're not caring about how much it wins. Yes, so it is ordinal. But of course, when I go to repeated games, it becomes cardinal. I have 5 minutes left. I will not be able to say much. But certainly in the models that I have presented so far, the normal form games, one-shot games. It is purely ordinal construction. Yeah. In terms of real-world games where efficiency, so there's a long tradition in economics, right? Going back to Adam Smith, the idea of the invisible hand is actually this that going back even before to Mandeville and the Fable of the Bees, that private pursuits will lead to this is the liberal argument, from Locke to Hayek, basically that you leave people free to pursue their own self-interest, you'll end up with greater social welfare, right? There's a tradition coming from, of course, Smith is a complicated figure. He has got lots of things that don't speak to that or don't go in that direction, but this idea of the invisible hand, that people are led as if by an invisible hand to pursue an interest that serves society while it is also serving their own. This tradition, it's there in Smith, although there's a lot else in Smith, but certainly it is there in the sort of English liberal philosophers and certainly in Hayek. So there they see the game, capitalism in sense, as a game in which private pursuits of self-interest is actually social welfare enhancing. So that's just kind of a bit of a pompous answer to your question, but basically, yeah, there are people who don't see in the real world as many efficiency equity trade-offs. On the other hand, there are people that see us destroying the climate and say, how can it be? Individual self-interest is just going to kill us all. So, you have these views. Yeah. Maybe there is. Maybe there is. Maybe there is. Certainly. So your point yesterday was in low-dimensional systems, because you can, of course, you can get chaos in continuous time with if you go above 3. Yeah. Yeah. The low-dimensional system, as we saw yesterday, discrete framework gives you very different dynamics. You get very different dynamics. My answer would be yes. Is there any point in looking at it? Yes, I would say yes. I have not done it, but I would say yes. It might be something interesting there, actually. At least with regard to convergence to non-point attractors. Yeah. In fact, what the reason I went through the all-pay auction is really to show you exactly how complex it is. It's deceptively simple. It looks like, it's kind of simple that, you have some probability with which actions are chosen, sampling equilibrium, the likelihood of an action being selected under sampling should match the likelihood with which it is being chosen. You can say it in words. But once you start saying, okay, is the Nash equilibrium sampling in all-pay auctions, you start to see that you have to look at all the possible events that could rise to a particular winner versus another winner, and it is complex. But the theory of sampling equilibrium, which, like I said, there's only a handful of people working on this, although it's growing. The idea is not that people compute these events at all. It is that they actually try out stuff, and then you get behavioral heterogeneity. So everybody's doing something very simple, and sampling equilibrium describes the distribution that emerges as a result. So, for example, I'll give you the example that I'll repeat the example I gave yesterday, which Ariel Rubinstein gave when he presented this idea 20 years ago in a seminar. He said, he was coming from Princeton to Columbia. He said there's 3 ways to cross the river, the Hudson River. And, there's the Holland Tunnel, the Lincoln Tunnel, George Washington Bridge. You have to do one of those 3, otherwise you can't reach the island. And, how do I decide these things? And like I said, it's the pre-GPS era. You try the tunnel, you try the second tunnel, you try the bridge, you get stuck in traffic in one place, in another place you breeze through, and that's it. That becomes your habit. We do this a lot. Think about how often we behave like this. In New York and in most cities, including Bangalore, there are so many restaurants. There's so many bars. How often do we go to places we've never been to before? We find something that works and we stick to it. Even if you go to that restaurant that you have been to, it may have 50 items on the menu. How often do you actually try something other than your favorite? Something that worked for you before the last time. So this way of making decisions is really, I think, quite common. And it's not very complex. In fact, it is a way of dealing. Oh, yeah. Yeah, from a computation. It's extremely complex, and in fact, I try to. And once you get to repeated games, which I'm out of time, so I'm going to stop. But I'm not going to talk about repeated games. It gets massively complex, and from the point of view of the analyst, yes. But if it captures the way in which people are making decisions, then we are forced to study it. Yeah. Let me just, one second, let me just see if there's anything I want to say, because I'm out of time. I just wanted to make sure that this is the repeated game. So, repeated games, it would take a whole new lecture to finish that. It's an interesting thing, direction, which is a new direction for sampling equilibrium, but I'm going to skip just through all this. There's no way I can do all this. Maybe what I'll do is I'll show you 2 things. I'll just show you 2 things. Just think of I want to show you. This is a prisoner's dilemma, right? So think about. I'll just show you 2 things about the repeated game, and I want to show you the sampling equilibrium in repeated game. This is a prisoner's dilemma. Cooperation. If you both cooperate, you get 1. Both defect, you get 0. But defection, if one defects, the other cooperates, you get better, right? So you know this thing. This is a particular prisoner's dilemma, all right? Imagine that this thing is repeated 100 times. It's a finitely repeated game. Nash equilibrium doesn't change. You still get defection in every period if you just apply Nash. It's not intuitive, but that's the prediction of the theory. what does sampling equilibrium predict? Now it's complicated because now you have to look at sampling strategies. You don't just sample cooperation defection, it's a repeated game. So, so you're sampling in the repeated game. Now, what is a strategy in a repeated game? It's a plan of action. Even if you restrict attention to strategies that depend only on what happened one period before, like tit for tat, like the trigger strategies, there are still 26 unique strategies actually in the business dilemma. Here are some of them. Do I have time for a few? Do I have a few minutes or no? Huh? No, because I started a little bit late, and I'll stop anytime you want. What is the time actually? Now it is 10:50, and it was supposed to be 9:30 to 10:45. Give me 5 minutes. Give me 5 minutes. I'll just give you the summary. No. 5 minutes is all I need. Here are some examples of strategies in the repeated business dilemma. So here you start with cooperation. If the opponent defects, you go to defection, and you never come back. Right? This is called sometimes the grim trigger strategy. This is tit for tat. You start with cooperation. If the opponent defects, you defect, and you keep defecting until they cooperate, then you come back. This is tit for tat. Right? Very famous strategy. Here's a strategy where it's very forgiving. You start with cooperation. If the opponent defects, you defect for one period, and then you come back, even if they still defect. So even if whether they defect or cooperate, you just punish them once and you come back. And then if they defect again, you go back. So this is a strategy. Here's another strategy. You cooperate. If they defect, you go to defect. And then if they cooperate, you keep defecting. This is actually quite an exploitative strategy, although it's quite nice to start. But if they defect, you come back to cooperation. It's a weird strategy, but like I said, you can't ignore a strategy. You have to actually use your equilibrium concept and say what will emerge from your analysis. You can't just say this is a stupid strategy, I'll assume that people don't use it. Right? You have to apply the concept of sampling equilibrium and say, look, will any of these strategies exist in a sampling equilibrium? Right? There are 26 strategies actually. Some start with defection, some, etc., etc. Right? Let me just show you. I'll just show you what is sampling equilibrium in the repeated business dilemma. I was going to show you more than this, but okay. So this is it. This is a sampling equilibrium. In the repeated business dilemma, out of the 26 strategies, this last one is the one that always defects actually. These are ordered in terms of their binary representation. I don't have time to go through all of that, but this one is the grim trigger strategy. So this will cooperate, but then if you defect, it just goes. So it has about 10% frequency. So this is the mixed strategy distribution over the 26 strategies in the iterated business dilemma. So every one of them is actually present, even those weird ones, although some of them have very low frequency. But they have a positive probability of being selected under sampling. Yeah. Yeah, but there are some games in which so basically this is suppose you start, and this is stable. So if you start with any arbitrary distribution of strategies, the sampling dynamics take you to this every time. I've tried lots of different initial conditions, and this is what it takes you to. Very quickly, I'll show you one more game. I should really stop here. I'm testing your patience, but let's look at a repeated coordination game. So this is what's called a coordination game. There's an equilibrium where both choose high, equilibrium where both choose low. They're both equilibria. And this x can be very large. So this is quite risky. If x is, let's say, -5, let's say, this is quite risky because if you choose high, the other person chooses low, you're going to get a very low payoff. But you can see, high is best response to high, low is best response to low, right? Again, you get 26 strategies because, it's one period history. This is, you can represent that with 26 different unique strategies in this thing. But in this case, stable sampling equilibrium looks very simple. looks like this, which is basically you get an equal weight on the first five. The first five, what are these strategies? These are strategies that begin with high, and as long as the other person keeps playing high, you stay with high. Right? If the other person plays low, then these strategies start to differ in terms of what they do. So they're different, but they never play low until the other person plays low. And in the prisoner's dilemma, the corresponding thing is you never defect until the other person defects. Now that's not stable. You get this distribution that I showed you. For repeated coordination, you do get this kind of thing over here. Yeah. They're all zeros. They're all zero. Sorry. The reason why it's not showing as zero is because it's a numerical simulation and we haven't converged yet. So this is, if I run this, yeah, exactly. So Yes. It's not like quantum response where everything has positive probability. No. In this case, the sampling equilibrium has literally zero on a whole bunch of strategies. Yeah. So the last slide is the message I'd like to leave you with. Basically, is that that even though I've tried to sort of sell this notion of sampling equilibrium to you, I would rather finish on a more modest note, which is that there will be situations in which it doesn't make sense to apply. And Nash equilibrium works really well in many situations. In certain situations, level K works the best, which we looked at, or variations of that model. But there are certainly some situations in which sampling is worth a look. That's the message I want to end on. Yeah.